Good morning, students. So in last class we are discussing about what? Metallurgy. So we are discussing about metallurgy. In the metallurgy, 3 points we discussed. So what is the first process? So purification of ore. So this is completed. What are the important points? So already we seen what is that? Heim-of-Rowley. So hydraulic washing, magnetic separation, froth flotation and leaching process. So that is already completed. Second point. Preparation of crude metal. So preparation of crude metal, otherwise impure metal. So this is also we are completed. So what are that? Ore. So oxidation or reduction. So in oxidation, so that is what? Calro. Next in reduction, smelting process. So Calro smell. So calcination process or roasting process or smelting process. In this we have Ellingham diagram. So now we are going to discuss about Ellingham diagram. So next after that the third process. What is the third process? Refining of metal. So refining of metal. So now after Ellingham diagram we are going to discuss about purification of metal. So now we will put a heading Ellingham diagram. So what is the main importance of Ellingham diagram? So without doing any other experiments, directly by seeing the chart, so which is reduced to which metal, we can easily find out. So Ellingham, scientist introduced. So Ellingham diagram, it is the combination of thermodynamic concept. So thermodynamic process. So whatever the reaction spontaneously takes place, so that is explained by thermodynamic. How that is spontaneous? So spontaneous reaction. So that is explained by Gibbs free energy. So what is the Gibbs free energy? Delta G equal to delta H minus T delta S. So standard temperature means you take delta H naught T delta S naught. So here, so we are taking Gibbs free energy versus entropy change. If we take this one graph, so on x-axis, so x-axis you take T delta S, so temperature. So temperature we are taking, so T delta S, here delta G. So delta G naught versus temperature is the main graph between these two. So here, different examples we will see here. So first, one by one. See, first one. Example, if metal is converted into metal oxide. Suppose we are discussing here, so anything, halides, oxides. So now example we are discussing about oxides. So oxide compounds only we are taking example. Metal is combining with oxygen, you are getting metal oxide. So metal I am represented M. So this is O2, you are getting MO2 or MO, whatever it may be. See, this is what a solid, entropy 0. So there is no movement. Next, oxygen is gas, so entropy is present. So that is yes. Next, metal oxide, it is a solid, so entropy is 0. The change in entropy, delta S naught, equal to what? Product entropy minus this one. 0 minus S, you are getting a negative value. So you apply in the Gibbs free energy, delta G naught equal to delta H naught minus T into delta S naught is a negative value. So that's why delta H naught plus into T. So positive. So if you take the graph, so it is looking at y equal to mx, so plus c. So that means it is coming as a positive. So from starting C value, something is there, delta G naught here, temperature value. So you are getting up to here. So A to B. After temperature increasing, it is going to C. So when metal is become as a metal oxide, the Ellingham diagram, delta G naught, Gibbs free energy versus temperature. So is the positive slope. Next B to C suddenly increases. That means A to B indicates so solid form. A to B, the metal oxide is in the form of a solid. Next B to C suddenly increment. So that means this metal oxide become as a liquid. So after this temperature that become as a liquid. So liquid means what? Entropy increases. So suddenly that curve is increases. So this is next. Second example, you take carbon. Carbon react with oxygen become as carbon dioxide. So carbon is a solid. So entropy 0. Oxygen gas. So entropy you take S. 1 mole yes. Carbon dioxide also gas. This entropy also 1 mole. Delta S naught. That is S minus S. Product minus reactant. That is 0. So delta G naught equal to delta H naught minus T delta S naught. Delta S value 0. So that means delta G naught equal to delta H naught. So that's why. So how the graph is coming? So X, Y temperature. Next delta G naught. So this is the temperature is independent on this. So you are getting a straight line. It is parallel to the x-axis. So this indicates C plus O2 gives rise CO2. So that is. Next, third example. You take carbon monoxide. See, carbon monoxide react with oxygen. You are getting CO2. So 2 moles of CO, 2 moles of CO. Then, so here it is a gas, it is a gas, it is a gas. So entropy is there. It is 2 moles of entropy. Here 1 mole of entropy. Here 2 moles of entropy. So delta S naught that equal to. So product moles minus 3S. So that value is you are getting negative value. So delta G naught equal to delta H naught minus T delta S naught. So here delta G naught equal to delta H naught minus T into delta S is a negative value. So negative into negative. So you are getting positive. So delta G naught equal to delta H naught positive. So here also X into Y. Delta G naught temperature. This is also you are getting positive slope. So that is what 2CO plus O2 gives rise to 2CO2. This is. Next, suppose the formation of carbon monoxide. Carbon reacted with oxygen. Fourth. Suppose carbon reacted with oxygen. So you are getting carbon monoxide. So carbon is a solid, entropy 0. Oxygen gas, entropy is S. Carbon monoxide, that is 2S. So that means delta S naught. So 2S minus S, that is equal to positive sulfur. That is positive entropy is there. So delta G naught equal to delta H naught minus T delta S naught. So delta H naught minus of T here positive. So that's why delta H naught minus negative. Yeah. So here y equal to mx plus c. So delta G naught on y axis temperature. So here what happens in negative slope. So it is moving down. So that means 2c plus O2 gives rise to 2CO. So in Ellingham diagram, some are negative slope, some are positive slope, some are unaffected. So straight line parallel to the x-axis. All these are coming. So whatever we discussed, all the examples we put together in one diagram. So then you will get, that is the complete Ellingham diagram. So that means so x-axis we are taken temperature delta G naught. So y-axis. See metal. So metal becomes next another metal. Take B. Next some are coming as straight line. So that is C. Next, some are going positive only, D. Next, some are coming negative, so E. So like that, you take so many combinations, metal to metal oxide, carbon to carbon dioxide, carbon to carbon monoxide, carbon monoxide to carbon dioxide, any other metals. So in Ellingham diagram, what is the important? In this graph, below curved compound reduces above compound at that temperature. So that is important. Suppose you take here. So at T1 degree centigrade. So next at T2 degree centigrade. So at T1 what happens? Who is below? A is below. So at T1 degree Celsius, what happens? A compound is below, B compound is above. So A reduces the B. So below one reduces above. Next at T2 degree Celsius. So T2, who is the below? B is the below. So that means B reduces like A. So without doing experiments in the lab, by seeing this one, we can take which one is reduced to which one. Suppose you are taken C. So at T1 and T2 degree centigrade, what happens? A and B both are reduces C. So what you can write? At T1 degree centigrade as well as T2 degree centigrade also, A and B both are below the C. So A and B both are reduces C compound. So like that, below one reduces above one at that particular temperature. So now suppose you take T3. So here. So you take T3. So T3 what happens? C reduces E. Next you take T4. At T4 what happens? E is down, C is above. So at T3 C reduces E. At T4 E reduces C. So that is the importance of this Ellingham diagram. Next. So two processes we are completed in the metallurgy. Now we are going to discuss about the third process. So in the metallurgy, the third process is what? The refining of metal. Otherwise, preparation of pure metal from the crude metal or impure metal. So third process in the metallurgy, so that is preparation of pure metal from crude metal, otherwise impure metal. So this is also called as refining of metal. See, already we are prepared, fine the metal, refining, so purification of this. So here, which process are there? So that our shortcut. So Delhi, whole Beku, LMO, macro zone. See, the what are the process? Here one, distillation. Next, second, liquefaction. Next, third one, polling process. Next, fourth one, besimerization. Next, fifth one, cupellation. Next, sixth one, electrolysis. Next, seventh one, Mons process. Next, eighth one, Van Arkel's process. Next, ninth one, chromatography. Next, 10th one, zone refining. See, which of the following process is useful in the refining process or preparation of pure metal? So these are. So one by one we will see. Distillation. Distillation means it is depending on where? Boiling point. So liquefaction. Liquefaction means you convert into liquid. So it is depending on what? Melting point. So we will discuss one by one. So distillation. So distillation means what? The liquids are separated. So means that is depending on the boiling point. So in this third one is distillation process. So distillation means separation of liquids. Separation of liquid mixes. Generally we call it as a distillation. So where distillation takes place, so the elements which has a less melting point, that boiling point. Boiling point least. So least boiling point metals are purified. See, in the metals, which one has the least boiling point? So that is volatile metals. So which one you call as volatile metals? In your D block elements, second B, otherwise 12th group. What are that? Zinc, cadmium, mercury. So these are, in what way we are taking one slanting table. We are taking here. So metals, impurities. So impurity, metal. So metal, boiling point. So boiling point or melting point. Least melting point. So we are heating. So who are easily melted? So that is coming outside. So These also useful in liquefaction process also. So in liquefaction also, you can take a similar process. In liquefaction means that is depending on least melting point. So least melting point elements again you can take that one. So zinc, cadmium, mercury also. Next bismuth, lead. So these are also elements. So directly they will ask, so which elements are useful? So in that distillation means you think about the least boiling point, liquefaction means you think about the least melting point, what are them? Next, third. So polling process. See, polling process, the name itself, pole means, so that is a freshly cutted bamboo stick. See, freshly cutted bamboo stick we are taking. See here, bamboo stick means what? Organic material. So organic material is made up of with what? So that is a carbon and hydrogen only. So here carbon and hydrogen